to Professor Daqing Li, please.
Thank you. Then, so I'm gonna share the.
In the bottom of your screen, you see a green button, share screen. Okay,
You see it?
very good.
Okay. Can you hear me good?
Very good.
Okay. So thanks for the invitation. So I'm gonna use this precious opportunity to introduce my work, focus on the urban traffic. So the title of my topic is Health Management of Urban Traffic. Here we, especially in China, there are many mega cities where you have tens of millions of a population. So inside this city, you would have all kinds of management problems, which we call urban disease. For example, congestion, which is one of the major urban disease. We spend a lot of time on the road before the work. According to the estimation, so every citizen in Beijing would cost them 10,000 yuan for each year, only for the congestion. Not mention the air pollution and also the safety risk uh, brought by the congestion. So here we would like to understanding the mechanism of the urban disease, especially the congestions, by the method of complex systems. So for now, we have many internet companies who are also working on the same problems. For example, Alibaba, who developed the city brain in one of the major city of China, Hangzhou. So this city brain is supposed to solve the traffic congestions by the machine learning methods. Given Alibaba is one of the powerful internet company in China and all over the world. But the fact is there are even more traffic congestions after the optimization. Not only for Alibaba, like other companies, including Huawei and Didi, they also aiming at solving the problem of congestions from different angles. For example, Didi, they would like to solve the congestion by the smart transportation brain. So they claim they have two kinds of machine learning models. One is by the direct data driving method. Another is by some kind of a model driving method. This is what Didi do. And also Huawei are using their 5G technology to build the neural system of the smart city, where they wish to connect the car to cars and the car to the roads, and all of this together to make fast decision according to the real-time information. So all of these companies are performing some kind of traffic health management from the machine learning side. Meanwhile, when we check the reference of the transportation, we found mostly this reference are focusing on the traffic on the one-dimensional highway systems, mainly because before the transportation are well developed in country like Germany, like United States and Japan. So they focusing on build very efficient highway systems, which are mainly one-dimensional networks according to our view. That's why their method cannot be directly applied on our megacity two-dimensional and very complex road networks. That's the result this leading to the existing problems like huge computation cost if we want to calculate the reliability probability of one megacity. For example, in Beijing, there are 50,000 roads. If we only assume 2 states for each road, then the whole state of the city would be 2 to the 50,000, which is around 10 to the 15,000 states, which is already far beyond the current searching ability. So the present 2 methods, one is solely from machine learning. The other solely from the traffic flow theory developed by like German, United States and Japan scientists. So these 2 flows seems to have some gap for the Chinese own traffic congestion problems. That's how we go. So now we wish to develop the traffic congestion management method from measure the traffic reliability to understand the why and the how of the traffic congestions, and to provide the decision-making advice for the operator and also the users. For example, there are traffic index in different countries. For example, one of the most famous traffic index is called TomTom index, developed by United States. So they use this index to measure how many times a user spent on the road compared to the free flow situation. But this is purely from the user viewpoint, which is very much biased, because especially in China, this would only reflect the users who use the software of the internet company. So only them reporting the travel time information. That's why for a given megacities, the present measurement mainly reflect certain well-congested area instead of the whole city. So we focus us on the question of 3 main problems. One is how the congestion occurred. Second one is if you have a seed of a congestion, how this seed of a congestion spreading over the urban road networks. The third one is how this kind of congestion recover and disappear. So these are 3 main questions, which we call the reliability, vulnerability, and the resilience. If you see the figure below the page, then it's more clear. When we mean the occurrence of the congestion, we measure the reliability, especially from the network viewpoint, how the congestions influence the basic function of the city. And once you have a perturbation, for example, from the extreme weather or from certain emergency event, then the network would degrade to some lower level. How the network degrades, we call this the vulnerability. And after the degradation, through certain recovery methods, the network would recover maybe to its original level. This process we call the resilience process. So these are 3 questions we want to answer partially. The first question is how the congestion emerge. Congestion exists everywhere. This is very natural questions. But we want to ask one different questions. is there a city scale or network scale congestions, which would disentangle the whole traffic network? What do I mean? When one road becomes congested, you would consider this road is effectively removed from the original network. When you have more and more traffic flows into the whole city, then you would have correspondingly more and more roads congested, which are effectively removed from the original network. So this is like you perturbate or you delete the links in the classical percolation process. Then you would ask how many links a city can afford to lose to have the basic connectivity function for all the users. If you think about this, you can think this from an information network side. For example, if we want to measure if this Wi-Fi network over the conference room is good enough, we would ask if this Wi-Fi covered the whole space. The same as the traffic problem, because traffic is one public service. So the government or the operator would like to see how the basic traffic function cover the whole city instead of improving certain area or certain group of users from the system view. So we want to give a method to first to measure is this traffic provided by a given city good enough for all the citizens. So this is our purpose. We use the method of percolation. Percolation is one classical methods for the complex systems and the complex networks. I would assume most of you are very familiar with this. So percolation ask you can see the leftmost figure of the page. Percolation asks very simple questions. For a network, each node or each link is assumed to have two states, 0 or 1. So you would ask how many links or how many nodes you can remove to disconnect the whole networks. For example, if you see the left one, you will see P is 0.2. This is what we call occupation probability. It's like 20% of the nodes are connected. Then for this occupation probability, you would have only very small clusters, very small connected clusters. The whole network does not show the connectivity. When the P is increased to 0.8, you would have a giant component connecting most of the network nodes. So this is already well connected. For certain OD pairs, for certain origin and destination pairs, you would have a redundancy between these two pairs, more than one pass. Then there should be somewhere in the between. You have an occupation probability. The connectivity appear for the first time. In the physics, we call this occupation probability a critical point for the percolation. So this point marks the emergence of the global connectivity for a given network. Originally, this method is only applied on the two-dimensional lattice, one-dimensional lattice, very symmetrical networks from the physics. But afterwards, is applied in many realistic networks, including brain networks, the power grids, financial networks, social networks. There are many very famous papers on this. And as a Chinese, I would also introduce the game of Go. So this is like our version of the percolation. You have a very similar settings, and this is also famous for because the AlphaGo algorithm. So for each point, you have two kinds of nodes, black or white. So the criterion for judging the gain is when you have a giant white or black cluster could cover the most of the grids. But this is different from traffic. For the game of Go, there are only 19 to the 2 number of nodes, which is quite small. As I showed you in the previous slides, for Beijing network, you have a 50,000 rows. So the number of states in the system, in the row system, is much larger than the game of Go. That's why you cannot solve the transportation problem easily with only the machine learning methods. That's why I would say the mode or the percolation the percolation mode we found in the real traffic may help the machine learning methods to solve the traffic easier. So if you calculate the percolation, this will be the very first graph. The x-axis is the occupation rate. So as the occupation rate increase, the y-axis, which is the size of a functional cluster, is becoming larger and larger. Then you will see the critical threshold or critical point, separating the whole phase diagram into two parts. So with this, all the necessary introductions, I will begin to introduce what I found. First is traffic reliability. So for the traffic, what is the most different from classical percolation is the traffic is temporal, it's dynamical. Oh, 网络断了是吧? The traffic is temporal, it's dynamical, where the road condition or the road velocity is changing all the time. But at a given time, and a given snapshot of the road network, you would percolating the whole network with its road velocity. How? This Q is the relative velocity of a given road to its maximum value of a given day. So when Q equals to 0.69, which means this road have the 0.69 maximum velocity of its own during the day. So this Q is like your requirement for every road. When your requirement is very high, you need all the roads have the velocity above 0.69. Then you would have a very small number of roads available to you. You can see in the left figure, you have a very few roads available above the velocity threshold. But when your requirement is becoming lower, which is 0.19, then you would have most of the roads available to you. This is also very natural for your own driving experience. So if you want a very fast velocity, especially during the rush hour, then you would see very few roads and you will get trapped with your present velocity. But when you lower your demand, for example, to a very low value, then you would you can suffer most of the cities. So we want to ask one question, and this snapshot of the road network. So what is the critical requirement for the road to have the global connectivity of the road? What does that mean? When Q equals to 0.38, so at this critical point, you have the statistical connectivity of the road network, where most of the users can enter the roads with only the requirement lower than this value. This also means if you want the road above this critical point, then you would trapped definitely in some local connectivity high-speed clusters. So this Q equals to 0.38 is like we found some velocity limitation for the whole network instead of a single road. So this is our first findings. Of course, as the time goes, you would have a different critical point along the time. Then we found for two rush hours, morning rush hour and the evening rush hours, you would have a very similar critical points for different days. And also, you can, with this method, you can also identify the bottleneck roads, which appears only before and after the critical point. When you optimize this bottleneck roads, then you can increase the connectivity of the whole network. This is not like most of the studies in the traffic, which are from the past viewpoint. We also apply this method into the traffic reliability assessment under torrential rain. So you can see in the left, this is how the giant cluster we identified in the normal condition. And to the right, this is the giant component we identify under very heavy rain condition. This is a Wuhan city in 2016. So in this sense, you will find, especially during the heavy rain, the whole city is already out of the normal operation. So our second finding is about traffic vulnerability. When we first enter in the field of transition, the experts in the transport ask us, so would you find how the congestion spreads over the road networks? This is very popular words for the experts, but no one actually say how the congestion spreads over the road networks. So in our first attempts, we try this question from a model, from a very classical model, motor-like cascading overload models. So we attacked the center rows of a given lattice as shown in the top of the page. Then you would see the congestions or the overloads is spreading to the outermost of the networks in a not very ideal ring shape. But when you use certain methods to measure the velocity of this wave, you will find a very interesting thing is this velocity is very is constant over different network topologies. This is one surprising result to us, because before we would find we would assume this congestion spreading is very depending on its road networks, like many other dynamical process. But when we solved the model for the first time, I would say, in a theoretical way, we can confirm this finding. The propagation speed of the congestions. Of course, this is an ideal situation when you have only one congestion center in the center of the roads, in the center of the networks. You would find constant propagation speed. This also helps us even this is one model results. This helps us can explore the real congestion center in the Beijing city and many other cities from the real data. Of course, in the real case, this center have a different spreading abilities. For example, in the below, we can identify 7 congestion centers in the Beijing city, and each center has different infectious abilities of the congestions. So this work, we are still in the middle of the process. And from the large scale of the network, we also want to see how the network breaks when you assume the congestion as the perturbation. From the classical network methods, 不用动。And you would have two classical ways for the network to break. One is the random networks. So if you random perturbate this kind of networks, you would have a power law, cluster size distribution, and to the critical point. But for the scale-free networks, when you perturbate this kind of networks, first everybody knows you have a zero, almost a zero percolation threshold. And the second, because you have a zero critical point, so you don't have any critical behaviors for these scale-free networks. And the row networks different from these two classical case. For the row networks, we can find the Beijing city row networks are fluctuating from two modes, I would say. So one mode is identified mostly from the congestion, mostly from the rush hour. And in this mode, you will find the classical critical scaling in the two-dimensional lattices. The other mode is from the holiday and the non-rush hours. In the second mode, you will find the critical behavior very similar to the high-dimensional systems. So these two modes are switching all the time. You will see this interesting phenomenon for one networks for different times. You not only have different traffic volumes or traffic velocity, you could have two different universality classes. This is identified not only in Beijing, but also in Shenzhen. This kind of megacities. We also check this in a small city of China, Jinan. For this small city, we could only identify one universality class of the percolation. So we suspect this is because for the megacities, there are many superhighways inside the cities. And this superhighway behaving like a backbone of the road networks are fluctuating in different periods, which can switch in this universality class. The third finding is about, I have only 2 minutes, right? So I will go faster. The third finding is this here. We find the transportation not can show two metastable states. When you remove the most congested, for example, most congested 25% of the roads, for the classical percolation process, you would expect the similar one states. But for the real traffic, you can clearly identify two possible metastable network states. And we also identify them by the machine learning methods. I won't go to in details. And this is like the increases behavior, and you can see the stable behaviors between two critical points we identified by the scaling methods. Okay, I think I gonna finish my talk on time. So one sentence to summarize is we identify the traffic congestion complexity with the classical method of population and from the reliability, vulnerability, and resilience. And thank you.
Very good. Thank you, Professor. It was very interesting lecture. Is there any question from the audience? Let's ask something. Does your study have any real application in China or everywhere?
Yeah, we have a real application, especially in Beijing. Before Beijing measured the traffic reliability from how much the time users spend on the roads, so from the user viewpoint. Now we are helping them to measure how the city traffic goes from the population methods we just introduced.
Okay. Any other question? It's difficult to clap, but we can do this. It's a reaction from Zoom.
Oh, thank you. Thank you. Thank you.
Thank you for your
Very
presentation,
nice.
Professor.
Thank you.
Let's
Thank
go
you.
to another presentation. By Professor Vee-Liem Saw, and the title is Chaotic Semi-Express Buses in a Loop. Let's start.
Yep, thank you very much. Let me share my screen and play the video recording that I made earlier. All right, thanks. Hello, my name is Vee-Liem. I'm a research fellow at Nanyang Technological University, Singapore. I'll be speaking about our research on buses going in a loop, in particular a semi-express system, and investigate its chaotic behavior. So we have an internal campus shuttle bus service at NTU. This is a blue route, and this bus system is not efficient at all. In fact, it's common in any bus system in any major city that buses tend to bunch together. As you can see, this is a survey carried out at our university asking students what they think are the problems with our campus shuttle bus, and one of the issues raised is bus bunching. We have carried out quite a number of research in the past couple of years where we model our loop of buses, buses by a system of coupled oscillators. So the buses, they interact with one another because they pick up people at the bus stops. And we have concluded that the anti-bunch configuration, where the buses are not bunched, the buses are spread out, is an unstable system by comparison with the Kuramoto oscillators. So we can model this loop of bus stops, any generic loop of bus systems, by mapping it isometrically to the unit circle, which means that the distances on the loop is preserved. So you can see that the 12 bus stops here, they are fairly equally spaced out. And we also carried out a different approach where we implement reinforcement learning. Namely, the buses are allowed to figure out by themselves what is the best configuration to prevent bunching or to minimize the average waiting time of commuters for a bus to arrive. And one of the results that is pretty fascinating is the discovery of a semi-express system. So shown in this video is a simplified version or the simplest semi-express system where there are two buses, X and Y. They want to pick people up from A and B, and they want to send them to C. So X is a normal bus. It picks up people from both A and B and then sends them to C. Whereas Y is an express bus. It doesn't pick up people from A. It only picks people up from D and send them directly to C. So one is a normal bus and the other is an express bus. So we see that this is a semi-express system. And it turns out that such a semi-express system is more efficient than normal buses or express buses in terms of lowering the waiting time for commuters for a bus to arrive. And this is in fact the subject of the talk by Luca Vismara. So I urge you to attend his talk or try to catch a video recording of his if it's available. Now, we will first consider a simplified version of this semi-express system where the two buses, they only pick people up from A and B. X is the normal bus which picks people up from both bus stops, but Y only picks people up from D. No alighting is involved. We'll see that realistic system shortly after. So there are three situations because X picks people up from A and B, so there are two of them, and the third one is Y picking up from B. So the situations are the moment right when they leave their bus stops after picking up everybody. And for each of these situations, there are two possibilities because the phase difference could be less than pi or more than pi. So this gives us a total of 6 states, where a state is defined as the moment when a bus just leaves the bus stop and the other bus is not at a bus stop. Then we can enumerate by brute force calculations that this is the result, the state transition rules. There are 6 states, xa1, xb2 and so on. So xa1 refers to the state where x just leaves A and the phase difference is less than pi. So if you are at xa1, you can either end up bunching, so beta represents buses bunched at B, or you can end up with the state yb1. And this is worked out by brute force enumeration considering the possibilities. So this is the state xa1 where x just leaves A and the phase difference is less than pi. After this, the bus will be bus Y arriving at bus stop B, and then we need to calculate the time tau that Y stops at B, and this is again worked out based on the previous the historical paths. And there are two possibilities. If Y stops too long, then X will bunch with Y at B, or if Y just stops briefly enough, then X will not arrive at Y and Y leaves B. So these are the 6 possibilities. We worked it out by hand, brute force, and that's how we end up with this transition graph. One assumption is that when a bus is at a bus stop, the other bus can only traverse at most one other bus stop. That means the coupling is not too strong. So that's the state transition rules, and this is the result. So Ka and Kb, they represent the demand, how popular the demand at A and at B is. We keep Kb fixed at 0.01 and Ka is chosen to be some value, and the whole iteration is carried out, and then we repeat the iteration for many runs in increments of Ka increasing by 0.0005 up till this value, and this is the bifurcation diagram that we observe. So the result is that if Ka is less than Kb, the semi-express system cycles in periodic orbits, and we can actually calculate this analytically based on the state transition rules and find curves that exactly fit this part, here and here, where Ka is less than Kb. When Ka exceeds Kb, the system is evolving aperiodically. It's chaotic, as we'll argue later, but intriguingly there are fixed points. So these are the fixed points, the windows of periodic orbits in the midst of chaos. It's pretty reminiscent of the logistic maps bifurcation diagram. Now we'll move on to the more realistic A plus B to C system. Now there's a third bus stop C where people alight. X picks up from A and B, deliver them to C, but Y only picks up from B to C. Now there are 5 situations, and because there are 3 bus stops which are equally spaced out, there are 3 possibilities for each of these situations, namely whether the angle is between 120 degrees or 120 to 240 degrees or bigger than 240 degrees, giving us a total of 15 states. And again, the state is defined at the moment where a bus leaves a bus stop and the other bus is not stuck at another bus stop. Now this is the table of the transition rules. It is way more complicated than the AB system, and I cannot draw this in a plane, so I present it as a table. And we run the results, and we run the simulation, and we find similar results. However, there's no periodic orbits that's observed for all parameter values. This looks like very similar to the AB system, but it is in fact not a periodic orbit, because when you zoom into one of the points, sometimes it comprises two or more points, and when you zoom in again, it comprises two or more points, so they appear to form a fractal set. So what used to be periodic orbits when there is no alighting now becomes localized aperiodic orbits. You see these windows, it's a smear of points. And the reason for this is because now people have to alight. So for the buses X and Y, the number of people alighting depends on how many people they pick up. So there's this memory dependence which breaks the periodicity of the system. So that's a comparison between the AB and the ABC. AB has nobody alighting, and ABC is the realistic one where people alight. There are periodic orbits here, but this is not periodic orbits. So now we would like to calculate Lyapunov exponents. So we derive an approximate analytical map. The problem with the exact system that we enumerated is that the subsequent states, they are conditional upon historical states. That means you can get possibilities of the next outcome, and the time that buses stop depends on the historical path. So if we were to write this, which we actually did on a computer program, conditional statements is fine, but we cannot write this into analytical equations and try to calculate the Jacobian of the map. So to overcome this, we assume that the order of events are fixed, so they are not conditional upon the historical states, and we consider the longest tau amongst the possible taus. That means we consider the fact that the buses have to stop the longest possible time. Then we can get a 6D analytical map for the AB system and a corresponding 10D map for the ABC system. And with that, the Lyapunov exponents, they are easily computed. So this is the result of the map, where these 10 variables, they denote how long a bus stops as well as the phase differences. In the interest of time, I shall not go into those technical details, but this is the map. And you can see that there is this mod t, or 2 pi over omega, which is reminiscent of the Skinny Baker map as well as the 10th map, or this modulo 1 map. So these are well-known maps that behave chaotically, and it's no surprise that when we calculate the Lyapunov exponents, we find that the largest one is indeed positive for all parameters Ka, Kb, therefore indicating chaos for the semi-express bus system. So we see that the bifurcation diagrams, they are not exactly the same because of the assumptions that went in to derive the analytical map. Nevertheless, they're pretty similar. They capture the features. The analytical approximation does capture the features of when K is less than Kb, it's fairly regular, but when K exceeds Kb, the system transitions into chaos, and there are these windows where these they are localized orbits. So that's the conclusion. That's the results that I want to present here. And of course, as I mentioned, the motivation for this is because semi-express buses, they reduce the average waiting time of commuters better than express and normal express and normal buses. So let me conclude here by saying that, well, buses, they behave chaotically. In fact, there are known configurations where buses do indeed behave chaotically, and it's often seen as undesirable because you lose predictability of travel time and arrival time of buses. Nevertheless, here we find that the semi-express buses which behaves chaotically, they are in fact good because they reduce the average waiting times. And semi-express buses, they fix the assignment of buses to bus stops. It does not confuse passengers or the bus drivers, compared to other active strategies like no boarding or holding, where it can be confusing for the passengers and the drivers. And yeah, so those are the work that we have on this, are the references that we have on this topic. So let me conclude here, and thank you for listening. Hello.
Very good and very innovative work to present. Questions? Are there questions? No questions?
Hello.
You can ask directly or you can raise hands.
Hi, I have one question, if you can hear me.
Okay.
Yes, I can.
Yeah, so you're optimizing for the waiting time. Is there something regarding the carbon footprint or how much emission is there you are taking it into account?
Yeah, I think it's a similar question that I think you asked Luca Vismara in his talk. And I think
Yes.
yeah, Mr. Puneet, yes. I
Yes.
think he responded by saying that he will refer to you to one of the earlier papers that collected.
Yes, and
data.
I have not got the paper yet.
I see. He was trying to contact you, but he couldn't directly message you.
Okay, so
maybe, yeah.
we can get in touch. Actually, I'm also working on the same problem, so we can get in touch.
Okay.
Right.
Good. We'll look for you after
Sure.
this. Yeah. Okay. Thank you.
Other question? Thank you. Thank you.
Thank you. Yeah.
And the next one, the next presentation is by Professor Jean-Patrick Lebacque with the title Vehicular Traffic Under Conditions of Dynamic Assessment and Instantaneous Networks State Information as a Complex System.
Yes, okay. Hello, everybody. Could you please give me the screen share so I can share my screen?
You can put the green bottom.
Yes, it says l'animateur a désactivé le partage d'écran. It means that at this point, I'm considered a participant. So I think
don't know
it's...
if the host can do it. You have to press share screen. Do you see in the
yes,
bottom?
it is done there, yes. And when I share this, I push on this, I get this message that the host has deactivated the screen share for all participants.
I'm sorry. Can I just interact? This happened to me in another session. You should be assigned the co-host.
Yes, I am assigned co-host. It seems.
Yes, you should be.
Now I get it. Everything is okay. So I'm sharing my screen.
Okay.
A second.
Thank you.
Here we go. Thank you very much. I'm sorry for this tiny difficulty. Okay, so I'm Jean-Patrick Lebacque. So I'm from UGE, which is the University Gustave Eiffel, which has just been created a year ago. And so I'm from the transportation community. That's my expertise. And I'm going to talk about some traffic. So it is probably a rejoinder on the first presentation. Okay. Basically, the point of my presentation is to talk about the impact of information and the correlation between information and traffic and the impact of one on the other. Well, to give a little bit elements of background, before basically interaction between information flow was interaction between cars, like what we call car following. When you look at the car in front of you, the knowledge you got for a network through sheer habit, and basically the information you could get through panels, messages, and so on. Now the current evolution is extremely different because now you have lots of communication between vehicles, which is increasing by automation, autonomization, and so on. You also have lots of internet services, crowdsourcing, internet operators, and so on. And also some operators start using artificial intelligence to make prediction of traffic conditions and so on. So basically things change a lot now. Information and networks can be considered to propagate nearly instantaneously and long distance. So this changes completely the way networks function. And it has applications for management and planning. Well, so just to talk about planning a little bit and about management and traffic, what do you need? Basically, you need to know how many people are traveling, from where they come, where they're going, which is the classical distribution aspect. Then you need to know which mode they will choose, how they will travel. And then comes the gist of my talk, which is assignment, that is to say which path they choose to go to the destination and when they leave to do it. Okay, and so then of course you have traffic flow models, that is to say to describe how the traffic actually flows. Well, assignment, which is to say, as if you remember, choice of path and choice of departure time, comes in two big categories. It's the static case, so we're looking at average conditions, relatively stable conditions, which is the easiest and best understood. It has been well understood for, say, 25 years now. So basically, what's the problem? So you have demand for each origin destination, and then you consider that each traveler has some alternatives, the path he can choose, and the path has some quality, that is to say the cost, the travel time you need, eventually the financial cost, whatever. And so some example of the costs are given on the right of this slide. The bottom one being the BPR, famous BPR model for costs. Well, anyway, so for a long time, the basic idea has been the wardrobe principle that says, well, travelers are selfish, so they will choose whatever is best for them, the lowest cost path. Now, of course, if everybody chooses the same path, then the path stops being attractive, and so you have a matter of equilibrium between supply and demand. Well, in a mathematical, more mathematical way, it can be expressed as I've shown on this slide. Basically, if you consider the path costs, travelers will choose the lowest path cost, will choose the path with lowest costs, and they will not choose other paths. And in essence, you will have something like a fixed point problem, which actually you can represent as is shown on the right part of the slide, that is to say as a fixed point involving the travel cost, which here are denoted C or G, depending on whether it's by arc or by path. Well, so this has given rise, for example, with the work of Nagani, so some 30 years ago, and some ideas which are being pursued now, which is to represent this, to solve this fixed point problems by actually associating some field to this problem. What is the meaning of this field intuitively? If you consider, say, a field line, that would represent the learning process of a traveler, learning the cost of the network, and so going from one choice to the next by adjusting little by little, eventually changing a little bit his path and so on. The point, one of the main points, and this has attracted attention only for very little time, maybe 1 or 2 years, is the fact that indeed these fixed points may be very numerous, and they may not necessarily be stable. For example, this slide illustrates a case where we consider car and bus. So these are two different modes, but they share the same infrastructure, so they're in competition. And this example is obtained for simply two paths. So two paths, two modes. And so the horizontal axis is the flow of cars on the first path, and the vertical axis is the flow of buses on the first path. And so, as you can see, actually you get three different equilibria, two of which are stable, one of which is unstable. Now, this is not always the case, but it's definitely a possibility. The point is that if you consider a network where you have an enormous quantity of alternatives, and you may have several modes, especially now sharing the same infrastructure, then of course you may have an enormous quantities of fixed points. So this is the first point I wanted to make in my presentation. The second concerns now the dynamic aspect. So dynamic traffic assignment is much more complicated because not only you have to choose your path, say if you have a tiny network like the one that's depicted here in magenta, so you would need to choose your path in this, but also you have to choose travel time, and so the whole problem is expanded into time. This complicates things because one item is there are lots of paths in a network. Basically, the number of paths increases exponentially. The second point is that calculation of travel times is difficult because the travel time depend on time. And so, for example, if you consider a path with a sequence of arcs, so the travel time of the total path is actually the travel time of the first arc at the time of departure, plus then the travel time of the second, but at the time you enter the second arc, and so on. Basically, you have a semi-group structure, and so this complicates everything. What is worse is the fact that actually most agencies that communicate on travel time to travelers actually give what we call instantaneous travel time, which is an estimate of travel time at a given moment. So it has nothing to do with the real trajectory. This is illustrated by this slide, where a traveler which crosses, say, a link AB, his trajectory is in red. And so basically, you can define several travel times. You can define the experience travel time. That's the travel time that you know when you exit. Basically, it's an image of the past. You have instantaneous travel time. This is an image of the travel time at a given moment. And predicted travel time, that's what you would like to estimate when you enter the path. That's basically what the artificial intelligence methods try to give now. Well, so we have proposed some way to do this analytically. I will not dwell on this because I do not want to be too long. So I want to just look at some example where actually we compare the impact of giving instantaneous travel time and giving predictive travel times to drivers. The assignment we use is the so-called stochastic assignment, so it's slightly different from what I've given you by the fact that you consider that there is actually some kind of variability as far as the perception of cost are concerned. Well, so I'm going to give this example. So it's a 1OD, it is a 3-path. Basically, it is the region of Ile-de-France, and actually it is going from east of Paris to southwest of Paris. And so here, essentially, you have 3 paths, one in red, one in blue, and one in green, which doesn't show very well. That's the OD demand. And so the main point I want to make is this. If you give instantaneous travel times, actually, drivers make decisions not on what is actually going to happen to them when they travel, but actually what is given them at this instant. And so this creates actually a discrepancy, this creates problems. And here it shows, for example, for the various paths, you see the actual travel time, and the actual travel times you see are totally disconnected. Basically, the different paths are not synchronized. Whereas if you give them predictive travel time, then you get an image like this. And actually, one thing is important. Well, one thing is they're synchronized, which means traffic is well spread over the network. the second thing is that thanks to this, actually the travel times are much lower than the ones I had on the previous slide. The same shows when we check how many people, what's the proportion of people who choose one path or the other one. So in case when you use instantaneous travel time, they're totally desynchronized, whereas if you choose predictive travel time or something related, then they're well synchronized. So I'm going to pass this, and just to go to this one, which are the queue length. Here for this path, you have about 5,000 people in each queue, very desynchronized if you use instantaneous travel time, whereas actually you have about 3,000 and well synchronized the queues and well spread the thing. So it is very important to see that if you have this instantaneous travel time, it is liable to induce very bad instabilities. And actually, so what we're looking about is to see, for example, what kind of attractors we get in this case and so on. So I wanted to present a bathtub model, but okay, this is a model which is, I'll go back to the previous slide, which is a very simplified model to actually look at a very difficult problem, which is the problem of departure time choice. And so the bathtub model essentially is a model that's dynamic. It's a traffic model that's dynamic, and in which we forget about the precise dynamics in the network. That is to say, we do not look which path are used, we just look at their length. Essentially, that's the only parameter we keep. But on the other hand, we describe very well the departure time choice. So the model is quite nonlinear. Actually, the equations are summarized here. Well, they look a little bit bad. They're not very bad because you can use a Picard-like argument to show the properties. The only thing is the distribution that is looked for is the distribution of departure time of the travelers, which is called F in this slide, is actually a measure, but even with this, there are just a few technical difficulties. What I want to show is just a few results that actually you obtain. For example, if you consider a scheme in which travelers go by the information they had from the previous day, or they go by the information that an agency provides from the previous day, then actually you may get periodic orbits, like periodic choices, with some very bad assignments. And so this is illustrated, for example, here. So this is a criterion that estimates the quality of the assignment. And so actually here you see it's of period 3. But as well, we might also obtain something like this with a different starting point, which with the period 5, and so on. So this is very important. So here on the right, I illustrated also the number of travelers in the system versus time. And so here you see that actually indeed you have convergence towards 5 different states. So this means that the fact that there is no that there is a simple provider of information that is kind of similar in quality to the instantaneous travel time that I showed previously has actually very bad effects. Now, if there is some smoothing and some learning process that intervene, it is possible actually to smooth the solution. For example, here on the left, we have this quality of equilibrium that is described, and on the right, actually the states that we obtain. And so in the end, we obtain a state that is somewhat in the middle, which is actually not the best state possible. And here there is another aspect of traffic assignment, which is a dress-like paradox that intervenes. Well, this is it. So basically, what I want to insist on is the fact that when you have assignment, especially if you have multimodal assignment, then you can have many equilibria, you can have unstable equilibria, you have eventually have possible periodic states. And also the number of equilibria depends on the number of alternatives, which may make actually a huge number of equilibria that may not all be very distinguishable because some of them will be closed, some of them will not. All of this has actually serious implications on planning, and all this research actually is issued from work on planning. And so also another item I want to insist on is the fact that so the dynamics depend, of course, on choice behavior, and so choice behavior depends a lot on the information systems that's available, and so we have to be extremely careful in the future to check the way this information system actually impact the workings of the networks. The impacts may actually be very unfavorable. Already mayors are starting to complain, for example, of what is happening because Waze is derouting traffic somewhere they wouldn't really like, say in their backyard, but so things like this. So we have to be very careful and we have to take this into consideration for management. All right, that is the conclusion of my presentation.
Thank you. Questions, please?
I'm sorry, I went a little bit over time.
Okay, we started 3 minutes later. Question? Is there any question? Okay, thank you for the presentation. Thank you.
Thank you very much.
You're welcome.
Goodbye.
I think the session has finished.